Welcome back. In this slice of physics, we will discuss elasticity and Hooke's law. These concepts relate to the restoring force, also called the spring force, of elastic objects. These forces are responsible for a lot of day-to-day behavior we see around us, such as a ball bouncing on the ground, a tennis ball ricocheting off of a racket, and many other collisions. So let's take a closer look at these concepts. So let's take an example here where a spring lays on a desk and one end of it is attached to a wall. So as the spring just sits here with no horizontal forces acting on it, it attains a preferred length, and that length is called the equilibrium length. So we got here a length that's called the equilibrium length of the spring. So now let's see what the spring does if I stretch it or if I compress it. So here I take that spring and pull the right end to the right. So the spring ends up being stretched, and that's because of this force that I apply here pulling this end to the right. We know from experience that as we pull the spring to the right, it applies a force toward the left as it resists our pull and wants to pull it back to its equilibrium position. And this force of the spring that wants to take it back to its equilibrium position is called the spring force or restoring force. And if we take the example where I take that same spring and I compress it from its initial position, now I did this by pushing it in over here. And once again, we know that if I take a spring and push it in, it wants to push back out. And so the spring force in this case will act to the right, opposite the force that I'm applying. And it's this spring force here that we want to understand better. So let's take a look at what happens here. In this situation, when I pulled it, I have a displacement. So the original spring length was somewhere there. The new length is somewhere here. So the displacement to the right of the spring is that much. And let's call that delta x, consistent with our terminology from before for displacement. And in this case, I have that initial position here. So in this case, my delta x is towards the left. The displacement of the spring as a compression goes to the left. Now compare the direction of the displacement to the direction of the spring force. In this case, when it's stretched, these two directions are opposite. And in this case, when it's compressed, the directions of the displacement and the spring force are also opposite. So the first point we see here is that spring force is opposite the displacement of the spring. And we know that intuitively. Whenever I stretch a spring, it wants to pull back in. When I compress the spring, it wants to push back out. That's why it's called a restoring force. It wants to go back to the way it was in equilibrium. Second, we know from experiments that this restoring force or spring force is larger for larger displacements. So the more I stretch the spring, the harder it fights back, and the more I push it in, the harder it fights back. And I'm going to call this spring force F spring. And so we know that the spring force or restoring force is directly proportional to the magnitude of displacement. And then third, we know from experience that all springs are not equal. Some springs fight back harder than others. So there's this thing called spring stiffness, which depends on how the spring is made, and that spring stiffness affects the amount of restoring force. The higher the spring stiffness, the harder it fights back. And the spring stiffness is quantified by a measure called the spring constant. That only depends on how the spring is made, and it's simply a measure of how hard or soft the spring is, and it's written with a lowercase letter k. And we know that the force of the spring restoring force is also directly proportional to the spring constant. Okay, so those are our three summary points. Now, Hooke's law is an equation form of these observables. So Hooke's law simply states in equation form that the force, restoring force of a spring, denoted by F underscore SP, equals minus K delta x. Now to be clear, this force is a vector, the delta x displacement is a vector, and the spring constant K is a scalar. So let's see if this equation here is consistent with our observations that we made before. So number one, it said the spring force is opposite the displacement, so this negative sign makes sure of that. Whatever the direction of delta x, the direction of the spring is going to be negative that. So that's what tells us that they're opposite in direction. Number two, the spring force is directly proportional to the magnitude of the displacement. So if I just take delta x and increase it from, let's say, 2 centimeter extension to 4 centimeter extension, the force with which the spring pulls back will double. And thirdly, it also says that the spring force is directly proportional to the spring constant K, which means a stiffer spring that's made to be harder spring will fight back more for the same displacement. And by the way, the SI unit of the spring constant K is Newton per meter, so that when you multiply it by displacement, the distance units will cancel and you'll be left with newtons, which is the unit of force. Let's take a quick example to see how this Hooke's law works. So let's say there's a bed here, and you may know that a lot of the box springs and even some of the mattresses have springs in them. That's what gives them the cushiony feel. And so here's my mattress, and it's got springs inside like that. And let's say all of these springs are identical, and they have a spring constant of 400 Newton per meter. And when you lay here, let's say your head is on that spring, your shoulders are on this spring here, and your feet are on this spring here. Now, do you think the weight of your body is supported equally by all these springs, or do some of these springs bear more of the weight? Well, you may know intuitively that the spring that's supporting the edge of your foot or your hand supports less weight than the one that's supporting your shoulder or your head. So let's take two springs in this example and say a spring here supports 5 newtons of your weight, and a spring near your foot somewhere here supports 2 newtons of your weight. So let's see what the displacement of these springs will be. I can use Hooke's law, which was F equals minus K times delta x. Delta x is a vector, F is a vector, and for this spring here I can put in my force of 5 newtons equals minus 400 newtons per meter, that was my spring constant, times delta x, which we want to determine. So to solve this, you divide through by the K on both sides, actually minus sign and the K on both sides, which will give us minus 5 over 400, and the unit will be meters. The newtons will cancel and the meters will come to the top. And this gives us an answer of minus 1.25 times 10 to the negative 2 meters, which is minus 1.3 centimeters, where I have rounded the answer to 2 significant digits to be consistent with my inputs. And so this tells us that the spring that's supporting your shoulder here and supporting a weight of 5 newtons will be compressed by 1.3 centimeters. The negative sign simply means that the displacement is in the negative y direction here, corresponding to the restoring force that's opposite that in the positive direction as it supports you. That's your spring force here. And then if we look at the spring that's closer to your foot, that's only supporting 2 newtons of force, and we use Hooke's law for that one, we get 2.0 newtons equals minus 400 Newton per meter times delta x2, let's call this that, and that gives you delta x2 equals minus 5 times 10 to the negative 3 meters, or minus 0.5 centimeters, showing that that spring near your foot that's supporting lesser weight is compressed only half a centimeter, while the one that was closer to your shoulder supporting 5 newtons of weight was compressed by 1.3 centimeters. So in this slice of physics, we looked at elasticity and Hooke's law, which tells us about the restoring force or spring force and how it depends on parameters such as displacement and the spring constant.